What I want to do in this video is approach derivatives in a more visual way, in the way that I actually started approaching derivatives when I was first dabbling in calculus. So let's start with a function like f of x equals sine of x. Now the derivative of sine x doesn't seem obvious at first, but let's just see what we get. So what I mean by estimating the derivative is we're going to use tangent lines to look at the values of those tangent lines' slopes. We just jumped to another example, don't worry about that. What we're going to do is we're going to use these tangents and find their slopes, and then look at the derivative as being the slope of the tangent just visually. So, for example, here sine x has two extreme values. It has -1 over here and 1 here. Now the tangent to this curve looks like it's 0. It touches it just once. It just seems to be a horizontal line. So that means that the function, whoever's derivative is of sine x, should at 1, or at like this same point, pi over 2, be equal to 0. So we're going to put a big point here for 0. I see the coordinates are a bit kind of off, but let's just use this shape, because all we care about right now is the shape, not the actual values, because we're estimating. Now here at the bottom, it also seems to be 0. So we're going to put that down. Now, what about at this point at the left? Well, this looks kind of like the line y equals x, right? Some of you may have learned in the past that sine x looks kind of like x for small angles of 0, which means that it does look kind of like y equals x, whose slope is 1. So let's put down a 1 over here, all right? And don't mind this point over here. We're going to just get rid of that because that's a bit misleading. But there you go. How about here? Well, here, it seems that because sine increases and decreases evenly, or at a kind of equal pace, it seems that this line here should be similar to this line over here. And if this line was y equals x, then this line looks like y equals -x, which obviously has a slope of -1. So let's put that down. We're going to put -1 over here. Now, I would encourage you to keep in mind the values at which sine is high and low and in the middle, and look at the values that it corresponds to. So when sine is at its high at pi over 2, then the derivative is at 0. Meanwhile, when the sine is at its low of -1, the derivative is also 0. But when sine is at its middle, then this derivative function is at its high. So let's see. Here, this seems to be the same side of sine that's coming from the left over here. So we can say that it has about y equals x. So, joining the graph together, it looks like this function is gradually steepening until it becomes 0, and it steeps down more and more. So let's just estimate a graph. And it looks kind of like this. And wait a minute. This looks a lot like a function we already know. This looks a lot like cosine. So the question is the derivative of sine x cosine? Recall the definition of the derivative for a function. Remember that d dx, or the derivative of a function f of x, with respect to x, is defined to be, which is this little triangle on top of the equality signs, the limit as some h goes to 0 of f of x plus this little value of h minus f of x over h. All right? And in fact, I'm just probably going to do this. There you go. What this means is that, remember that if the derivative is a tangent, is the slope of the tangent, then if we take 2 points and we draw a secant line between them, then we get their average rate of change. But if we so let's just say this is point x, and this point here is x plus h. That means that if we bring h closer and closer to 0, then this point over here is going to go closer and closer to our fixed point x, which should create a tangent line as a secant line joins at one point. So that's the intuition behind the derivative, the visual intuition for a derivative. So let's look at that. So we have sine, so this is equal to the limit as h goes to 0 of sine of x plus h minus sine of x over h. And of course, plugging in h right now is going to give you sine of x minus sine of x, which is 0, over h, which is 0, which equals indeterminate form. So what can we do? Well, remember that the sine of a sum of two angles is equal to, I'm going to write that real quick, sine of alpha plus beta, right, is going to be equal to sine of alpha cosine of beta, right, plus sine of beta cosine alpha, sort of switching places in the second term or the first term, depending on how you like to write it. So anyways, we're going to use that. So this is going to be the limit. I'm going to write L as h goes to 0 to signify the limit as h goes to 0 of the expression here is going to be sine of x times cosine of h. Now, be careful that this h is within the cosine. It's a variable. It's not that cos h or cos, which is the hyperbolic cosine function. And you have plus sine of h. So again, this is not sinh, the hyperbolic sine. Rather, it's just sine of a variable h, cosine of x. And that's all taken over h. Now, what can we do at this point? Oh yeah, I'm sorry, minus sine of x. Don't forget the sine of x. All right, now at this point, we can split this limit, and actually we're going to be losing some space because we're kind of jumping into the next exercise. But this is going to be the limit as h goes to 0 of two different functions. And I'm going to split it like this. We're going to do sine of x, cosine of h, right, minus sine of x over h, plus the limit as h goes to 0 of, over h again, sine of h cosine of x. Now, why do I do this? Because watch this, and we're gonna ignore the bottom for now, because that's gonna be another exercise. But we can split this again. So the right hand side over here is gonna be a product of two limits, which is gonna be equal to the limit as h goes to 0 of sine of h over h times the limit as h goes to 0 of cosine of x, which since x is not dependent on h, and since h doesn't depend on x, the cosine of x in terms of the h world is a constant. So this just becomes cosine of x. And we know the limit as h goes to 0 of sine h over h. It's 1. So this entire expression is equal to cosine of x. Meanwhile, here, we can factor out a sine of x, right? And that's exactly what I'm going to do. So I'm going to just factor out the sine of x. All right? Sine of x times cosine of h minus 1. And then we can split this into a product of two limits. We can say this is equal to the limit of sine of x as h goes to 0 times the limit as h goes to 0 of cosine of h minus 1 over h. And now, remember that in the h world, sine of x is a constant, so this becomes just sine of x. But then notice that the limit as h goes to 0 of cosine of h minus 1 over h is equal to 0. That's one of the famous limits as well. So this whole term goes to 0, which leaves us just with cosine of x. So indeed, the derivative of sine x is cosine of x, and we just proved it. Which is a very cool idea, that the cofunction of sine is also its derivative. So that's a very important property. Now, can you do the same for cosine? Now we're going to do a different exercise, though. Instead of actually using the derivative definition to prove this limit, or prove the derivative of arctan x here, another cool function, we're going to just visually interpret it. So, right here, we see a line that looks kind of like 1. So we can say it's kind of up there at 1. But notice how the function is always increasing in value, which means that the function's derivative will never be negative. And notice how it's getting closer and closer to 0 each and every time, which means that we can do something like this if we want to approximate the function here. Because as you can see, it's going to trail off to infinity, and it's going to get closer and closer to 0, because this slope gets more and more dull and closer to a horizontal line, literally the horizontal asymptote. Now, on the other hand, this slope is also positive, and it's getting duller and duller and less steep as we go to negative infinity, which means that the function is, since this is an odd function, we can see that we get this sort of even-looking function as the derivative. And it's true, the derivative of an odd function is an even function, and vice versa. So this is the little function that's going to be the derivative of arctan x. Now, if you put into Desmos, I encourage you to kind of find out what this function could possibly be, because it's very interesting. All right, now we're going to do f of x is equal to the log of absolute value of x. Now, again, the absolute value of x here just means that you're treating negative values of x as positives, and you're just reproducing the same function. It's also called the even maker because it turns the function even. As you can see, because the absolute value of x is equal to the absolute value of negative x, right? So anyways, we can take a look at the log and see that it grows slower and slower as you go to infinity, right? Which means that the slope of the tangent line is going to get progressively more and more horizontal. Now, note that the log actually does still go to positive infinity as x goes to infinity, but that's not relevant to the slope of the tangent line. It's just going to go to infinity at an exponentially slower pace, if you will. So that means that whatever the end behavior of our derivative is going to be somewhere near 0. The horizontal asymptote will be 0. Now let's take a look at this function over here. There's a line here that looks like it could be like 1, maybe, over here somewhere. So we can put a 1 over here, or just put it over here. All right? Now the same goes, except it doesn't. What I mean by same, meaning that the same function is 1 over here. It's not, because the slope over here is always increasing, which means the function will never be negative. But here, the slope is always decreasing. It's getting more and more negative and steeper negative, which means that the function at this point is always negative. So we can put a -1 over here where we have a 1 here. And using our intuition of the fact that the derivative of an even function is an odd function, we should get an odd function. So if over here we see the slope is getting more and more positive infinity, we can see that the function goes from positive infinity like this and trails off to 0 over here. And again, because this is reflected on the opposite side, and that this function should be an even function, we can say the same like this. But wait a minute, this function looks a lot like the function 1 over x. And indeed, you will prove later on in your calculus course that the derivative of the log of an x and the log of absolute value of x will be the function 1 over x. But visually looking at this function, it's not obvious until you start estimating the tangent lines. And that's a very cool fact. Alright, so what have we looked at so far? We've seen that arctan is an odd function and that the derivative should be an even function, because of that kind of idea of f of negative x equals f of x, or negative f of x. Now, my question to you is, can you prove that the derivative of f of x such that f of x follows the notion that f of negative x is equal to negative f of x, this is the definition of an odd function, is that equal to some function g of x, where g of negative x is equal to simply g of x, which is the classification of an even function. So in other words, just prove that the derivative of an odd function is even. How would you go about doing that? And then also, we can start thinking about other ideas of derivatives, right? How do you prove that the derivative of the function log of absolute value of x is 1 over x? It's clearly visible here, but it definitely seems tough to do. So visual intuition is really important when we graph functions and when we graph their derivatives and see their rates of change. Now, I have 3 exercises remaining for you guys to do independently to just get a better idea of what it means to have a derivative as a slope of as defining the slopes of tangents and the rate of change of a function. So my first function that I would like you to first graph on Desmos and then use Desmos to accurately, as best you can, estimate those tangent lines and draw the derivative of the function is a function that looks like this. And this function is not the cubic x cubed. It's actually something that we've sort of referred to already today. It's the hyperbolic sine of x, sinh of x. All right? Now, estimate what the derivative of this function looks like, and then plug into Desmos d dx, sinh of x, to see what the actual function is. Then, I want you to take a look at the function e to the x. Now, this function is special for a reason, and if you estimate what the derivative is going to look like when you take its derivative by looking at the tangent lines, you should see a very cool and very special property that no other function has. So this is e to the x. And again, then when you're done with that, you can look up d dx, e to the x, to see how close you got from your paper to what's actually the graph. And finally, I wanted you to take a look at the function absolute value of x. That looks like this, right? And the key here is to sketch out the derivative on paper, and use Desmos to take a look at what the absolute value of x really looks like. And then in Desmos, put d dx, so the derivative of absolute value of x with respect to x, and see what you get. Is it what you expected? Did you do your estimations correctly? So again, these are just some exercises to do optionally, but I really encourage you to try out, just for fun even, finding random functions and sketching out / estimating their derivatives. If anything, you could also take your own functions that you made up, right? That looks something like this even, like this, who knows, and just estimate their derivative. Now this one looks very painstaking and even I wouldn't do that, but you get the point. You can create your own arbitrary functions and sketch their derivatives using approximations and visual intuition. So I hope this gave you a pretty good idea of how to look at derivatives in a visual way and seeing some special connections between certain functions. See you next time.